Hello, and welcome to the lectures on inflation. This is part one of the series on inflation. In this lecture, we'll give some symbols and definitions that will be used to describe the concepts of inflation. We'll present some trends for the U.S. economy, show some examples of price indices and conversions using those, and last we'll talk about the implications for the minimum attractive rate of return. Let's start with our definitions. Everybody knows what inflation is, but let's define it precisely. What this means is that it's an increase in the price of goods and services with no change in quality. And this last part, no change in quality, is important because sometimes it's very hard to compare things from one year to the next or 10 years later. Automobiles are a good example. Everybody knows that the price of autos has increased dramatically in the last 10 or 15 years. But if you reflect upon the type of automobile that you have today, you'll realize it's a different type of car. For example, it has more safety features. Well, that's going to drive up the cost. It has fuel injection. Well, that's going to make it more expensive, but better for the user in terms of fuel economy. You have more accessories on the cars. It may be impossible today to find a car with a manual transmission in some model lines. And of course, cars today last longer because of rust proofing and other types of materials. Even something as simple as bread may have changed in processing over the last 20 years. Nevertheless, economists try to do their best to compare prices for the same product with no change in quality. A price index is a measure of this type of inflationary increase with respect to some type of baseline. In the U.S., the baseline typically is taken to be 1983. In some instances, it may be 1967. The constant dollars is an abstract concept that is used by economists for defining purchasing power and prices for goods based on a baseline year. And last, we have actual dollars. This is what most of us see when we pay something in cash, or we write it on a check, or there's a fund transfer. This is the actual number of dollars that gets transferred from buyer to seller. Let's start with some examples. Our first example is for a 10-speed bicycle. Now let's imagine that in 1970 this bicycle cost $90. For the same quality bicycle in the year 2000 we might find a price of $218. So the change in price from 90 to 218 over 30 years, from 1970 to 2000, can be traced back to an average inflation rate of 3% per year. We take the 1.03 factor, we raise it to the 30th power, multiply that by the 1970 price, and we get the 2000 price of $218. Let's look at another example, a price index for medical care. Well, in 1998, the price index for medical care was 238.1. That's compared to an index value of 100 in January of 1983. Where did this information come from? It came from a website, BLS, Bureau of Labor Statistics. Well, let's continue with these examples. Price of the 10-speed bike in the year 2000 is $90 in year 1970 constant dollars. We'll go to the second type of example. Let's imagine we have a hospital stay of 5 days in 1998. And if that costs $3,000 in actual dollars in 1998, then we would have expected the same hospital stay, but in 1983, to cost $1,260. Or if we want to talk about the year 2000 and measure the cost of that hospital stay in 1983 constant dollars, and we take the actual dollar amount, $3,000, divided by the price index, 2.381, and get the amount $1,260. That's in year 1983 constant dollars. This is a simple computation because 1983 is the base year, and the price index for that was 100. Let's look at another example. Let's look at lumber over a 10-year period, in 1989 to 1999. In 1989, the price index was 125.7. In 1999, it was 179.5. So that's the difference over 10 years. Let's imagine that a typical 3,000 square foot home required $15,000 of lumber, that's raw material lumber, in 1989. And we want to know how much lumber would that house require if it were constructed in 1999 using the same building practices, same quality of construction? That may be hard to find today because everybody's using particle board instead of real wood. But let's imagine that we can still find somebody building a home in 1999 to the same quality, the same materials as in 1989. Well, what we'll do is we'll take the higher price index, the later price index, the 179.5, divided by the index for 1989, come up with a ratio of 1.428, multiply that by the $15,000, that's the 1989 cost of lumber, and we get $21,420. That would be the raw material price for the same home, same quality in 1999. Notice what we did. We took the price indices for the two respective years and we moved forward in time. Most of the time these price indices are going to be increasing. Occasionally they'll be declining. Let's look at some other types of products. We'll start with the solid line right here in the middle, starting in 1987 and moving forward 11 years, or maybe 12 years. Well, that's all consumer products. So you can see the trend there for all consumer products starting from the 87 time period. Look at the dashed line, that's the lowest line here. That's for food products. So price of food has been increasing, but not as much as all consumer products. You may be spending more on food, but perhaps you're getting more prepared items, whereas 10 years ago perhaps you were getting basic ingredients and doing your preparations yourself. Or you may be spending more in restaurants, but the basic food prices for things like milk, bread, meats, and things like that that you buy and then prepare at home have risen at a rate lower than the general rate for all consumer products. This heavy dashed line right here in the middle is for motor vehicles. So they've gone up, but not as much as all consumer products. The last line here is for medical care. Everybody knows medical care costs have been growing so much faster than everything else, and this chart is just a reflection of that phenomenon. Again, these indices are from the BLS website and the government page. Let's make some observations. The earnings rate on U.S. Treasury bills, a Treasury bill is an obligation from the U.S. government to an investor, whether it's a private investor or an institutional investor, where the government is borrowing money and the investor has a very safe investment. Well, that rate is approximately 2.5% to 3% above the general inflation rate. That's just an observation, and that's held true for the last 50 or 60 years. Along with that, we can make a similar observation about the growth rate, earnings rate on common stock, and that's generally 6 to 7% above the inflation rate. That doesn't mean you should immediately go out and buy stock, because you have to be very careful which stocks you invest in. The difference between stocks and Treasury bills is that the rate for Treasury bills is pretty stable. The rate for stocks, well, it varies all over the place depending upon which stock you have and what time period it is. You have upswings and downswings in the economy. You really need to balance your investments into a portfolio and have a professional manager. Let's have some more definitions. Market interest rate is that rate which is earned on actual dollars in the financial market. If you go to a bank and ask them what's the rate for certificates of deposit, they're quoting you a market interest rate. You go to a mutual fund manager and ask them what's the growth rate of the fund, they'll give you a market rate. It's sometimes called a nominal rate, sometimes it's called an inflation-adjusted rate. We'll call it a market rate in these lectures. The other important definition is real interest rate. And here's another situation where economists take an ordinary English language term like real, give it a very specific technical meaning that confuses most people. The definition of a real interest rate is a measure of the earning power of money measured in constant dollars. Now, we said constant dollars generally are not observable. We can observe actual dollars, and then we have to back out through some arithmetic to find out what the constant dollars are. And then we have to do more arithmetic to find out what the real interest or the real growth rate was. Sometimes this is called an inflation-free rate. Now we come to our fundamental relationship. And this is one of the key concepts in this lecture. And that is that the market interest rate factor is equal to the real interest rate factor multiplied by the inflation factor. So here on the left, we've got the real interest rate factor, 1 plus I prime, inflation factor, 1 plus F, and we get the market interest rate factor 1 plus I. That's the fundamental relationship that holds true for all of these inflation analyses. Remember, the market rate is what we observe in the market. The inflation rate is something that's observed by statisticians and economists. And the real rate is something that has to be backed out using this relationship. Let's look at some examples. Let's imagine the market interest rate is 12%. If the inflation rate is 3.5, then we can back out the real interest rate. We take the factor for the market interest rate, 1 plus 12, divided by the factor for the inflation rate, 1 plus 3.5%, and that gives us the factor for the real interest rate. Of course, we subtract 1, and that gives us the percentage, 8.213. So this reflects the increase in purchasing power each year if you have a market rate of 12% on your investments and inflation rate's 3.5. You're really earning this much in terms of purchasing power. Let's have another example. Let's say the minimum attractive rate of return is 20%. The company has decided that this is what they really want to earn on their investments when the economy has an inflation rate of 3%. Again, using the fundamental relationship, taking the 1 plus 20%, that's the market rate factor. Now we're talking about the minimum attractive rate of return. Divide that by the inflation factor, 1 plus 3%, subtract the 1, and then we get 16.5, the percentage, for the real minimum attractive rate of return that this company might be using. What happens then is if that inflation is forecasted to increase at a higher rate, let's say 6% instead of 3%, then the minimum attractive rate for actual dollar analysis should be determined as follows. We use the fundamental relationship. We take the real MARR factor, that's the real factor, 1.165, multiply that by the inflation factor, subtract the 1, and then we get the minimum attractive rate of return that should be applied to actual dollars of 23.5%. Let's work a numerical example here that's a little bit longer. Let's say we have a parent that needs to be cared for in a retirement home. And we wish to deposit a large sum of money to take care of our parent for the next 8 years. And let's imagine that the annual expenses are about $22,000 a year. We have an investment fund that's generating 8%. However, the medical care expenses, we're talking about, retirement care, would increase about 5% a year. So we want to know how much do we have to deposit now into an account. This is really a present worth problem, but now we have an inflationary environment. Let's work this problem using actual dollars. We said the care expenses are going to go up at 5% a year. So in year 1, instead of costing $22,000, they're going to cost $23,100. We've simplified the cash flows in this example to assume that all the cash flows are at the end of the year. In year 2, the $22,000 expenses would be factored up by the inflation factor for 2 years. So we can get year by year the actual dollar expenses. So in year 8, instead of $22,000, the actual dollars would be $32,504. So these are the cash flows in actual dollars year by year with end-of-year cash flow assumptions. Now we have a discount rate of 8%. We say that our market interest rate is 8%. We can take these actual dollars, $23,100, bring it back to time 0 using an 8% factor. This is the P/F factor. The second term, of course, is brought back using the factor for 2 years. The last term, $32,504, that's discounted back 8 terms, 8 years. And we get a total of $155,369. That's the total amount we'd have to deposit as a lump sum into an account. That's the analysis using actual dollars. Now let's work the same example using constant dollars. Well, the constant dollar expenses are just $22,000 per year. We can compute a real interest rate as follows. We can take the market rate factor divided by the inflation factor for this particular cash flow and compute a real interest rate that's 2.86%, or in decimal form, 0.0286. Then we can apply that to discount all the terms. So we can take the first term, the 22,000, bring that back one time period. The second term, bring it back 2 time periods. The third, bring it back 3. And when we do that, we get the same total amount. We get the same total, 155,369. Of course, we could have used a series present worth factor in this example because the 22,000 doesn't change. But what we did here is we used constant dollars and a real discount rate much lower than the market rate, and we got the same numerical value. So we have a very important observation. Both methods of analysis, the actual dollar analysis and the constant dollar analysis, lead to the same numerical present worth amount. The reason for that is the consistency between the market interest rate and the real interest rate. And that's, of course, related through the inflation rate using our fundamental relationship. We have some more observations. Real interest rates tend to remain fairly stable. However, inflation rates vary. So many times it's easier to perform the analysis using constant dollars. You can do the analysis with constant dollars, and then any present worth amount that you compute will tend to be the same regardless of the inflation rate. This holds for stable economies. It doesn't hold for economies that have inflation rates of 80% per year or more, because then you have other side effects going on that we've not considered here. And it ignores the effect on depreciation expenses, because depreciation is a tax-deductible item. We don't get the same tax benefits in an inflationary environment. So that's sort of a side condition that we have to either ignore if it's a small amount, or if it's important, then we have to go deeper into the analysis. So what have we done in this lecture? Let's summarize. We've talked about inflation. We've defined inflation. We've defined price indices. We had some examples of price indices. We defined this abstract term called the real interest rate, which is based on the market rate and the inflation rate through our fundamental relationship. We defined constant dollars, and we've given examples showing how actual dollars and constant dollars can be converted back and forth from one another. We had examples with price indices. We had an example where we computed the present worth using both constant dollars and actual dollars and got the same numerical value. And last, we had some observations about the stability of real rates and the convenience of using present worth, of computing present worth using constant dollars.